Welcome to ZzScience. Before we begin, allow your body to relax, your breathing to slow, and your mind to gently drift. Tonight, we explore science, quietly, calmly, and without urgency. There is nothing you need to do, only listen. In the very beginning, there was nothing but potential. Then, in a single moment beyond all measure, the universe came into existence. Not with sound, for there was no air to carry vibrations, and not with light, for light itself had yet to find its way through the dense fog of energy that filled all of space. This was the Big Bang, though the name suggests something far more violent than what truly unfolded. It was not an explosion in space, but rather an expansion of space itself, a gentle unfurling of reality from a point of infinite density into the vast ocean of existence that surrounds us now. In those first impossibly brief fractions of a second, the universe was extraordinarily hot and dense, filled with pure energy that blazed with temperatures beyond anything we can easily comprehend. But even in those earliest moments, there was a kind of order, a set of physical laws beginning to take hold, guiding the young cosmos through its first transformations. The fundamental forces that govern all interactions began to separate from one another, each taking on its own distinct character. Gravity, electromagnetism, and the nuclear forces all emerged from what had been a unified whole. And in this separation, the seeds of all future complexity were planted. As the universe continued to expand, it also began to cool. This cooling was gradual by the standards of those first moments, yet it happened with extraordinary speed compared to anything in our everyday experience. The temperature dropped from values that would vaporize any known substance to levels where the first particles could begin to form stable relationships with one another. Quarks, the fundamental building blocks of matter, found themselves drawn together by the strong nuclear force, combining in groups of 3 to form protons and neutrons. These particles, collectively known as baryons, would eventually become the hearts of all atomic nuclei. But in those early moments, they simply drifted through the cosmic soup, buffeted by photons and surrounded by electrons. For several minutes after the beginning, the universe remained hot enough for nuclear fusion to occur freely throughout all of space. Protons collided with such energy that they could overcome their natural electric repulsion and bind together, forming the nuclei of the simplest elements. Hydrogen nuclei, consisting of single protons, were by far the most common, but some fused together to create deuterium, a heavy form of hydrogen with both a proton and a neutron. A small fraction of these deuterium nuclei went on to form helium, the second lightest element, with 2 protons and 2 neutrons bound tightly together. Even tinier amounts of lithium formed during this brief window of cosmic house, nucleosynthesis, and then, as the universe continued to expand and cool, the fusion stopped. The temperature had dropped below the threshold needed for these nuclear reactions, and the elemental composition of the universe was set for hundreds of millions of years to come. But the universe was not yet transparent. Despite having cooled enough to stop nuclear fusion, it remained far too hot for electrons to settle into stable orbits around atomic nuclei. Instead, electrons zipped freely through space, and whenever a photon of light tried to travel any distance, it would collide with one of these free electrons and be scattered in a new direction. Light could not travel far before being deflected, and so the universe was filled with a luminous fog, opaque and glowing, with no clear lines of sight extending beyond a short distance. This era would continue for hundreds of thousands of years, with matter and radiation locked together in a dense, hot plasma that filled all of space. During this time, tiny variations in density were already present, subtle ripples in the distribution of matter that would eventually grow to become galaxies and clusters of galaxies. These fluctuations were incredibly small, differing from the average density by only 1 part in 100,000, but they were real and persistent. In the denser regions, gravity worked to pull more matter inward, ever so slowly increasing the concentration of particles. In the less dense regions, matter was slightly more spread out, creating gentle voids that would eventually become the vast, empty spaces between galaxies. But all of this structure was still embryonic, waiting for the right conditions to develop. The universe continued to expand, and as it did, it continued to cool. The temperature dropped steadily, and finally, after approximately 380,000 years, it fell below a crucial threshold. At this point, electrons had slowed down enough that they could be captured by atomic nuclei, forming the first complete neutral atoms. Hydrogen atoms, with a single electron orbiting a single proton, became the dominant form of matter in the universe. Helium atoms, with 2 electrons orbiting their heavier nuclei, made up most of the rest. This process, known as recombination, fundamentally changed the nature of the cosmos. With electrons now bound inside atoms, photons suddenly found themselves able to travel freely. The universe became transparent, and light could stream across space without being scattered. This moment is preserved for us today in the form of the cosmic microwave background radiation, a faint glow that comes from every direction in the sky. When we observe this radiation, we are seeing light that has traveled for more than 13 billion years, light that was released when the universe first became transparent. The photons that make up this background radiation have been stretched by the expansion of the universe, shifting from visible light, microwaves, but they still carry information about the conditions in the early cosmos. The tiny temperature variations in this radiation map out those primordial density fluctuations, showing us the seeds from which all cosmic structure would eventually grow. After recombination, the universe entered a new phase, one that would last for many millions of years. The cosmic fog had lifted, and light could travel freely. Yet there were no stars to shine, no galaxies to glow with the light of billions of suns. The universe consisted of vast clouds of hydrogen and helium gas, slowly drifting through space, gradually being pulled by gravity into denser and denser concentrations. This was a time of darkness, not because light could not travel, but because there were no significant sources of light. The cosmic microwave background provided a faint glow, but it was rapidly fading as the universe expanded and cooled, and soon it would dim to the point where it contributed almost nothing to illuminating the cosmos. This period is known as the Cosmic Dark Ages, and it is one of the least understood eras in the history of the universe. No direct observations from this time have reached us because no stars had yet formed to produce the light that might be detected. We can only infer what happened during these dark ages through careful study of the conditions before and after, through sophisticated computer simulations that model the behavior of gas and dark matter, and through the faint traces that this era left on the structure of the universe we see today. What we know suggests that this was a time of slow, inexorable change, as gravity worked patiently to transform the nearly uniform distribution of matter into the seeds of cosmic structure. The dark matter, a mysterious substance that does not interact with light but does exert gravitational influence, played a crucial role during this time. Dark matter particles, whatever they might be, began to clump together under their own gravity, forming vast halos of invisible mass scattered throughout the universe. These dark matter halos acted as gravitational wells, deep points in the fabric of space where ordinary matter, the hydrogen and helium gas, would naturally flow. The gas fell inward toward the centers of these halos, slowly accumulating and increasing in density. As it did so, it began to heat up, converting gravitational potential energy into thermal energy, warming the gas as it compressed. For millions of years, this process continued in darkness. Gas clouds grew larger and denser, pulled together by gravity, occasionally colliding and merging with one another. The universe was a quiet place during this time, devoid of the energetic processes that would later light up the cosmos. There were no exploding stars, no active galactic nuclei, no brilliant nebulae glowing with the light of young, hot stars. There was only gravity, working slowly and steadily, drawing matter together into ever more concentrated forms. As the gas clouds contracted, their central regions became denser and hotter. In the very deepest parts of the largest clouds, where the most matter had accumulated, the pressure and temperature began to climb toward critical values. The atoms in these regions were moving faster and colliding more frequently, pressed together by the weight of all the gas above them. The cores of these proto-galactic clouds were becoming furnaces, places where conditions were approaching those necessary for nuclear fusion to begin once again. And then, after perhaps 100 million years of darkness, something extraordinary happened. In the densest cores of the largest gas clouds, the temperature and pressure finally crossed the threshold needed to ignite nuclear fusion. Hydrogen atoms were pressed together with such force that their nuclei overcame their electric repulsion and fused, releasing tremendous amounts of energy in the process. The first stars were born, and with them, the universe was illuminated once more. These first stars were different from the stars we see in our night sky today. They formed from gas that contained only hydrogen and helium, with none of the heavier elements that would later be produced inside stars and scattered into space. This pristine composition meant that the gas could not cool as efficiently as it can today, because elements like carbon and oxygen, which help gas clouds radiate away energy, were not yet present. As a result, the first stars were massive, perhaps dozens or even hundreds of times more massive than our Sun. These enormous stars burned brilliantly and briefly, fusing hydrogen into helium at prodigious rates, flooding the universe with ultraviolet radiation. The light from these first stars began to change the universe around them. Their ultraviolet photons were energetic enough to ionize hydrogen atoms, stripping away electrons and creating bubbles of ionized gas that expanded outward from each star. As more and more stars formed, these bubbles grew and eventually overlapped, gradually reionizing all the hydrogen in the universe. This era, known as the Epoch of Reionization, marked the end of the cosmic dark ages and the beginning of a new chapter in cosmic history, one in which light and energy from stars would play a central role in shaping the structure and evolution of the cosmos. The first galaxies began to form during this time, though they were small and irregular compared to the grand spiral and elliptical galaxies we see today. These early galaxies were chaotic collections of stars and gas, often colliding and merging with one another as they moved through space. Each collision would trigger intense bursts of star formation as gas clouds were compressed and fragmented, creating new generations of stars. The massive first-generation stars lived fast and died young, exploding as supernovae after only a few million years. These explosions scattered the first heavy elements in space, enriching the surrounding gas with carbon, oxygen, silicon, iron, and all the other elements that would be essential for the formation of planets and eventually life. Dark matter continued to play its invisible role throughout this process, providing the gravitational scaffolding upon which visible matter could accumulate. The dark matter halos that had formed during the Dark Ages grew larger as they captured more matter and merged with other halos. The largest of these halos became the sites where the biggest galaxies would form, drawing in vast amounts of gas and giving birth to billions of stars. The cosmic web began to take shape, a vast network of filaments and clusters connected by tendrils of matter, with enormous voids in between where very little material could be found. Our own galaxy, the Milky Way, has its origins in this early era of galaxy formation. It began as a relatively small collection of stars and gas, one among countless similar structures forming throughout the young universe. The exact details of its birth are still being pieced together by astronomers, but we know that it formed gradually through the merger of many smaller proto-galaxies over hundreds of millions of years. Each merger added new stars and gas to the growing structure, and with each addition, the Milky Way became a little larger, a little more massive, and a little more complex. In the beginning, what would become the Milky Way was probably an irregular, chaotic system, with stars moving in many different directions and no clear overall structure. But as time passed and more material was added, patterns began to emerge. Angular momentum, the tendency of rotating objects to keep rotating, caused the gas to settle into a disc-shaped configuration, with most of the material orbiting in roughly the same plane around the galactic center. Stars that formed from this disk-bound gas inherited its rotational motion, creating a flattened distribution of stars that would eventually become the galactic disk we see today. Not all the stars followed this pattern. Some of the earliest stars, those that formed before the disk had fully taken shape, remained in more random orbits, creating a roughly spherical halo around the galactic center. These halo stars are among the oldest objects in the Milky Way, relics from the very earliest stages of our galaxy's formation. They contain very small amounts of heavy elements, reflecting the fact that they formed from gas that had been enriched by only a few generations of supernovae. By studying these ancient stars, astronomers can learn about the conditions in the early universe and trace the history of our galaxy back to its beginnings. The process of building the Milky Way was not smooth or uniform. It happened in fits and starts, with periods of intense activity followed by quieter times. Smaller galaxies were captured by the growing Milky Way's gravity and torn apart, their stars scattered into streams and clouds that would eventually mix with the rest of the galactic population. Some of these smaller galaxies contained globular clusters, dense balls of hundreds of thousands of stars that remained bound together even as their parent galaxy was destroyed. These globular clusters still orbit the Milky Way today, ancient witnesses to long-vanished galaxies. Over billions of years, the Milky Way settled into a more ordered state. The disk became thinner and more defined, with gas and young stars concentrated in a relatively flat layer, only a few thousand light-years thick, but extending tens of thousands of light-years across. Within this disk, a beautiful spiral pattern emerged, with graceful arms winding outward from the galactic center. These spiral arms are not fixed structures, but rather density waves, regions where stars and gas are temporarily concentrated as they orbit the galactic center. Stars move into the arms, spend some time there, and then move out the other side. But the arms themselves persist, maintained by the gravitational interactions among billions of stars and the dark matter halo that surrounds them. The galactic disk is a place of ongoing creation, a cosmic nursery where new stars are constantly being born. Vast clouds of molecular hydrogen, mixed with dust particles made of carbon, silicon, and other heavy elements, drift through the disk, providing the raw material for star formation. These molecular clouds are cold and dark, with temperatures only a few tens of degrees above absolute zero, and they can contain enough mass to form thousands or even millions of stars. Within the largest of these clouds, gravity causes the gas to fragment into smaller clumps, each of which may eventually collapse to form a star. The process of star formation is gentle in its early stages. A small region within a molecular cloud begins to contract under its own gravity, very slowly at first, taking thousands or even millions of years to make significant progress. As it contracts, the density increases and the gravitational pull becomes stronger, accelerating the collapse. At the same time, the cloud begins to spin faster, conserving angular momentum as it shrinks. much like a figure skater spinning faster when they pull their arms in close to their body. This rotation causes the collapsing cloud to flatten into a disk, with most of the material concentrated in the center, but a significant amount spread out in a rotating disk around it. In the very center of this contracting cloud, the material becomes denser and hotter. The pressure builds as more and more mass piles on top, and eventually, the temperature climbs high enough for nuclear fusion to begin. At this moment, a star is truly born, beginning its long life of converting hydrogen into helium and releasing energy that will shine into space for millions or billions of years. The young star is often still surrounded by the disk of material from which it formed. And this disk may go on to form planets, moons, asteroids, and comets, creating an entire planetary system around the newborn star. These star-forming regions are among the most beautiful sights in the galaxy. When viewed through telescopes, they appear as glowing nebulae, clouds of gas illuminated by the intense ultraviolet light from hot, young stars. The radiation from these stars causes the surrounding hydrogen gas to glow with a characteristic red color, while dust particles scatter blue light, creating intricate patterns of light and shadow. Some of the most famous nebulae in the night sky, such as the Orion Nebula and the Eagle Nebula, are active star-forming regions within the Milky Way, places where we can witness the birth of new stars in real time. The process is not always peaceful. The most massive stars, those with dozens of times the mass of our Sun, produce intense stellar winds that blow vast amounts of material back into space. These winds, combined with the ultraviolet radiation from the stars, can actually halt star formation in nearby regions by heating and dispersing the gas that would otherwise collapse to form new stars. When the most massive stars reach the end of their brief lives, they explode as supernovae, releasing enormous amounts of energy and driving shockwaves through the surrounding gas. These shockwaves can trigger new rounds of star formation by compressing nearby gas clouds, but they can also disrupt and destroy star-forming regions, creating a complex interplay between creation and destruction. Despite this activity, the overall impression of the galactic disk is one of calm and order. Stars orbit the galactic center on roughly circular paths, taking hundreds of millions of years to complete a single orbit. Our Sun, for example, moves through the galaxy at about 200 kilometers per second, a speed that seems fast by human standards, but translates to an orbital period of approximately 225 million years. The stars maintain regular spacing from one another, rarely coming close enough to gravitationally disturb each other's planetary systems. Even in the densest parts of the disk, stars are separated by distances of many light years, ensuring that close encounters are extraordinarily rare. Near the center of the Milky Way, conditions are different. The density of stars increases dramatically as one approaches the galactic nucleus, and at the very heart of the galaxy lies an object of almost unimaginable nature, a supermassive black hole. This black hole, known as Sagittarius A star, contains approximately 4 million times the mass of our Sun, all compressed into a region smaller than the orbit of Mercury. It is invisible itself, as nothing, not even light, can escape from within its event horizon, but its presence is revealed by the motions of stars in its vicinity. Astronomers have tracked individual stars orbiting Sagittarius A star, following their movements over many years. These stars race around the black hole at incredible speeds, some reaching velocities of thousands of kilometers per second as they swoop past the point of closest approach. The orbits of these stars are highly elliptical, taking them from relatively distant regions down to within a few light hours of the event horizon and back out again. By carefully measuring these orbits and applying the laws of gravity discovered by Isaac Newton and refined by Albert Einstein, astronomers have been able to calculate the mass of the central object with great precision, confirming beyond any doubt that it is indeed a supermassive black hole. Despite its enormous mass, Sagittarius A star is remarkably quiet by the standards of supermassive black holes. Some galaxies contain black holes that are actively feeding on large amounts of gas, heating that gas to millions of degrees and causing it to emit brilliant radiation across the entire electromagnetic spectrum. These active galactic nuclei can shine with the light of billions of stars, making them visible across the entire observable universe. Our galactic center, by contrast, is relatively dim. Sagittarius A star is not currently consuming large amounts of matter, and so it produces only modest amounts of radiation, mostly in the form of radio waves and X-rays. This quiescence is fortunate for us, as an actively feeding supermassive black hole would make the galactic center an inhospitable place, bathing the inner regions of the galaxy in high-energy radiation that could be harmful to planetary atmospheres and potentially to life. The black hole does occasionally flare up, briefly brightening when a small amount of material falls too close and is consumed. Astronomers have observed these flares, which last only a few hours and increase the black hole's brightness by factors of 10 or more before fading back to normal levels. These events provide valuable information about the environment immediately around the event horizon, a region where the laws of physics are pushed to their extremes and where Einstein's theory of general relativity predicts strange and wonderful phenomena. Around the black hole, within the innermost few light-years of the galactic center, is a dense cluster of stars unlike any found elsewhere in the galaxy. These stars are packed much more closely together than in the disk, and they include some of the most massive stars known to exist. The exact conditions that allow such massive stars to form in this extreme environment are still being studied, but it seems clear that the intense gravitational field of the black hole plays a role, helping to compress gas clouds to the densities needed to form these stellar giants. Farther out from the galactic center, but still within the inner kiloparsec or so, is a region known as the galactic bulge. This is a roughly spherical distribution of stars, many of them quite old, that surrounds the galactic center and rises above and below the plane of the disk. The bulge contains billions of stars, and their collective gravity plays an important role in the dynamics of the entire galaxy. The stars in the bulge have more random motions than those in the disk, moving in all directions rather than following the orderly circular orbits that characterize the disk. This difference in motion reflects the different ways the bulge and disk formed, with the bulge representing an older, more chaotic phase of the galaxy's history. The spiral arms of the Milky Way are among its most striking features, though they can be difficult to study from our position within the disk. We are located about 26,000 light-years from the galactic center, roughly halfway out to the edge of the visible disk, and from this vantage point, it is challenging to map out the full structure of the spiral pattern. Nevertheless, through careful observations of gas clouds, star-forming regions, and the distribution of young stars, astronomers have pieced together a picture of the Milky Way's spiral structure. It appears that our galaxy has 4 major spiral arms, along with several smaller arm segments, all winding outward from the central regions. These spiral arms are not simply trails of stars left behind by some ancient disturbance. Instead, they are density waves, regions where the concentration of stars and gas is temporarily enhanced. As stars orbit the galactic center, they encounter these density waves, slow down slightly as they pass through, and then speed up again as they emerge on the other side. This slowing and speeding up creates a traffic jam effect, with more stars present in the arm at any given time, even though individual stars are constantly entering and leaving. The same is true for gas clouds, which become compressed as they enter a spiral arm, often triggering the collapse and fragmentation that leads to star formation. This is why spiral arms appear so bright and colorful in images of other galaxies. They are full of young, hot stars and glowing gas, the products of recent star formation. The spiral pattern itself is thought to be maintained by a combination of factors: the differential rotation of the disk with inner regions orbiting faster than outer regions, naturally tends to create spiral features. The gravitational pull of the Milky Way's stellar bar, an elongated structure of stars in the central regions, also contributes to the spiral pattern by creating gravitational perturbations that organize stars into the observed configuration. Additionally, interactions with satellite galaxies may play a role, as their gravitational tugs can create ripples in the disk that manifest as spiral features. Our Sun resides in a relatively calm region between two major spiral arms. We are located in what is sometimes called the Orion Spur, or the local arm, a minor arm segment that lies between the larger Sagittarius and Perseus arms. This location has likely been beneficial for the development of life on Earth, as it keeps us away from the intense radiation and frequent supernova explosions that characterize the more active spiral arms. The environment around our solar system is stable and relatively quiet, with no nearby massive stars that might threaten us with their violent deaths. The Sun itself formed approximately 4.5 billion years ago, a relatively recent event in the life of the Milky Way. By this time, the galaxy had already been forming stars for more than 8 billion years, and the gas from which the Sun condensed had been enriched with heavy elements from countless previous generations of stars. This enrichment was crucial as it provided the raw materials needed to form rocky planets like Earth and the complex molecules that would eventually give rise to life. The process of the Sun's formation began in a molecular cloud similar to those we observe today in star-forming regions throughout the galaxy. This cloud, which may have contained enough material to form hundreds or thousands of stars, was gently compressed by some external influence, perhaps the shockwave from a nearby supernova, or the passage through a spiral arm density wave. Whatever the trigger, a region within the cloud began to collapse under its own gravity. As this proto-solar nebula collapsed, it spun faster and faster, flattening into a disk with a growing concentration of mass at its center. The central region heated up as gravitational potential energy was converted into thermal energy, and after perhaps a few 100,000 years, the temperature and pressure at the core reached the point where hydrogen fusion could begin. The Sun ignited, beginning its long career as a main sequence star, a stable period that will last for about 10 billion years in total. But the Sun was not alone. The disk of material that surrounded it, known as the protoplanetary disk, contained more than enough mass to form all the planets, moons, asteroids, and comets in our solar system. This disk was a chaotic place, filled with dust particles and gas molecules constantly colliding and sticking together. Over time, these collisions built larger and larger objects, from microscopic dust grains to pebbles, from pebbles to boulders, and from boulders to mountain-sized planetesimals. The process of planet formation was gradual but inexorable. In the inner regions of the disk, where temperatures were high, only materials with high melting points could remain solid. These included metals like iron and nickel, and rocky minerals like silicates. As a result, the planets that formed in the inner solar system, Mercury, Venus, Earth, and Mars, are small, dense, and rocky. In the outer regions of the disk, beyond what is called the frost line, temperatures were low enough for water ice and other volatile materials to remain frozen. This allowed the outer planets to gather much larger amounts of material, forming the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. Jupiter formed first among the giant planets, and its presence had profound effects on the rest of the solar system. Its massive gravity stirred up the asteroid belt, preventing the material there from coalescing into a planet. Jupiter's gravitational influence also likely played a role in shaping the orbits of the other planets, possibly migrating inward and then back outward during the early history of the solar system, a process that may have scattered water-bearing comets into the inner solar system, delivering the oceans that would eventually cover much of Earth's surface. Earth itself formed through the gradual accumulation of planetesimals, a process that took tens of millions of years. As Earth grew larger, its gravity became stronger, allowing it to sweep up more and more material from its orbital neighborhood. The heat generated by these impacts, combined with the decay of radioactive elements in Earth's interior, kept the young planet molten. Heavy elements like iron sank toward the center, forming Earth's metallic core, while lighter rocky materials floated toward the surface, eventually cooling to form the crust. One of the most significant events in Earth's early history was a massive collision with a Mars-sized object. An impact so violent that it melted both bodies and ejected enormous amounts of material into orbit around Earth. This debris gradually coalesced to form the Moon, our planet's constant companion for the past 4.5 billion years. The Moon's presence has had important effects on Earth, stabilizing the tilt of our planet's rotation axis and creating tides that may have played a role in the development of life. In the early solar system, the inner planets were subjected to a period of intense bombardment, as leftover planetesimals and debris continued to collide with them. This heavy bombardment phase lasted for several 100 million years, pockmarking the surfaces of Mercury, Venus, Earth, and Mars with countless impact craters. On Earth, these impacts may have repeatedly sterilized the surface, evaporating any oceans that had formed and making the planet temporarily inhospitable to life. But eventually, the bombardment slowed, the surface cooled, water condensed to form oceans, and conditions became stable enough for life to emerge. The exact timing of life's origin on Earth is still uncertain, but evidence suggests that simple, single-celled organisms existed at least 3.5 billion years ago, and possibly even earlier. These early life forms were probably similar to modern bacteria, using chemical reactions to extract energy from their environment and reproducing through simple cell division. For billions of years, life remained simple and unicellular, slowly diversifying and adapting to the changing conditions on Earth's surface. Meanwhile, the Sun continued its steady burning, fusing hydrogen into helium in its core and maintaining the stable output of energy that makes life possible on Earth. The Sun is an unremarkable star by galactic standards, neither particularly large nor particularly small, neither especially hot nor especially cool. It is classified as a G-type main sequence star, commonly called a yellow dwarf, though the Sun actually appears white when viewed from space. Its mass is about 330,000 times that of Earth, and it converts about 4 million tons of matter into energy every second through the process of nuclear fusion. This might sound like a lot, but given the Sun's enormous mass, it can maintain this rate of consumption for billions of years. The energy produced in the Sun's core takes a long and winding path to reach the surface. Photons are constantly absorbed and re-emitted by atoms in the Sun's interior, bouncing around in a random walk that takes thousands of years to traverse the distance from core to surface. Once a photon reaches the surface, it can travel freely into space, carrying with it the energy that will warm planets and drive weather systems and, on Earth, power the process of photosynthesis that sustains most life. Earth orbits the Sun at an average distance of about 150 million kilometers, a distance that is sometimes called an astronomical unit. This is just the right distance for liquid water to exist on Earth's surface, placing our planet in what astronomers call the habitable zone, or sometimes the Goldilocks zone, where conditions are neither too hot nor too cold for life as we know it. Venus, our inner neighbor, is too close to the Sun and has become a hellish world, with surface temperatures high enough to melt lead. Mars, the outer neighbor, is too far away and too small to retain a thick atmosphere, leaving its surface cold and dry. Earth, in the middle, has thrived. Over billions of years, Earth has been home to an incredible diversity of life, from the simplest bacteria to complex multicellular organisms, from microscopic algae to giant trees, from tiny insects to enormous whales. Life has adapted to nearly every environment on Earth's surface, from the deepest ocean trenches to the highest mountain peaks, from frozen polar ice to boiling hot springs. Through all this time, the Milky Way has continued its slow rotation, and our solar system has orbited the galactic center perhaps 20 times since Earth formed, traveling through different regions of the galaxy, sometimes passing through spiral arms where star formation is active, sometimes drifting through quieter regions between the arms. The galaxy is not a static environment. Stars are constantly being born and dying. Gas is being recycled through repeated cycles of star formation and supernova explosions, and the distribution of matter is slowly evolving. The Milky Way is surrounded by a halo of dark matter that extends far beyond the visible disk, providing the gravitational glue that holds the galaxy together. This dark matter halo contains most of the mass of the Milky Way, yet it remains invisible and mysterious, detectable only through its gravitational effects. Within this dark matter halo, there are also streams and clouds of ordinary matter, remnants of smaller galaxies that have been torn apart by the Milky Way's gravity. Some of these streams can be traced back to specific dwarf galaxies that are still partially intact, slowly being consumed by our larger galaxy. The Sagittarius dwarf elliptical galaxy, for example, is currently in the process of being disrupted, and its stars are being spread out into long streams that wrap around the Milky Way. Eventually, these stars will mix with the rest of the galactic population, losing their separate identity and becoming simply part of the Milky Way. There are also globular clusters orbiting in the halo, dense balls of stars that each contain hundreds of thousands to millions of individual stars packed into a relatively small volume. These globular clusters are among the oldest objects in the galaxy, with ages of 12 to 13 billion years, formed in the very earliest stages of the Milky Way's history. The stars in globular clusters are almost entirely old, low-mass stars, as any massive stars that formed with them have long since died. By studying the properties of these ancient stars, astronomers can learn about the conditions in the early universe and test theories of stellar evolution and nucleosynthesis. The halo also contains a sparse population of individual stars, many of them also very old, moving on orbits that take them far above and below the galactic disk. These halo stars are thought to be remnants of the early, chaotic phase of the Milky Way's formation, stars that formed before the disk had settled into its current configuration. They have much lower abundances of heavy elements than stars in the disk, reflecting the fact that they formed from gas that had been enriched by fewer generations of supernovae. Some of these halo stars may even have formed in separate dwarf galaxies that were later absorbed by the Milky Way. Looking outward from the Milky Way, we see a relatively sparse environment. Our galaxy is part of a small group of galaxies called the Local Group, which contains about 80 galaxies in total, though most of them are small dwarf galaxies with only a few billion stars or less. The two dominant members of the Local Group are the Milky Way and the Andromeda Galaxy, which is similar in size and structure to our own galaxy, but located about 2.5 million light-years away. The third largest member is the Triangulum Galaxy, which is somewhat smaller than either the Milky Way or Andromeda, but still contains tens of billions of stars. These three spiral galaxies, along with their retinues of smaller satellite galaxies, make up the bulk of the Local Group's mass. The dwarf galaxies orbit around the larger galaxies, held by gravity, and many of them show signs of having been disturbed by tidal forces from their larger companions. Some are being stretched and pulled apart, slowly losing their stars to the larger galaxies. Others have had their gas stripped away by interactions with the hot gas that surrounds the larger galaxies, effectively halting their star formation and leaving them as slowly aging populations of old stars. The Andromeda Galaxy is approaching the Milky Way, moving toward us at a speed of about 100 kilometers per second. In approximately 4 billion years, the two galaxies will collide, though this will not be a violent impact in the way we might imagine. The vast distances between individual stars mean that actual stellar collisions will be extraordinarily rare. Instead, the two galaxies will pass through each other, their gravity causing massive distortions in both structures. Stars will be flung out into long tidal tails. Gas clouds will collide and trigger intense bursts of star formation, and the two supermassive black holes at the galactic centers will eventually spiral together and merge into a single, even more massive black hole. This merger will fundamentally change the structure of both galaxies. The orderly spiral patterns will be disrupted, and the final result will likely be a large elliptical galaxy, a smooth, roughly spherical distribution of stars with little or no ongoing star formation. By that time, most of the gas in both galaxies will have been used up to form stars or expelled from the system entirely, leaving behind a collection of aging stars slowly cooling over trillions of years. Our Sun, if it still exists at that time, will find itself in a very different galactic environment, possibly located far from the center of the merged system, perhaps in a quiet region where little has changed despite the dramatic events that transformed the galaxy as a whole. But that merger is still billions of years in the future. For now, the Milky Way continues its steady existence, a vast island of stars in the expanding universe. The galaxy rotates with a grace that belies its enormous scale, taking approximately 250 million years to complete a single rotation. Stars are born in the spiral arms, live out their lives over millions or billions of years, depending on their mass, and eventually die, returning their material to the interstellar medium to be incorporated into future generations of stars. The cycle continues, endlessly repeating, driven by the fundamental laws of physics and the pull of gravity. The interstellar medium, the gas and dust that fills the space between stars, is not uniform. It exists in different phases with different temperatures and densities. There are cold, dense molecular clouds where star formation occurs, cool atomic clouds where hydrogen exists as individual atoms rather than molecules, warm, partially ionized regions heated by the ultraviolet light from hot stars, and very hot, very low density regions blown out by supernova explosions and stellar winds. These different phases are constantly transitioning into one another as cooling gas condenses into clouds. Clouds collapse to form stars, and energetic events from those stars heat and disperse the surrounding medium. The element abundances in the interstellar medium have been gradually increasing over the lifetime of the galaxy. When the Milky Way first formed, its gas consisted almost entirely of hydrogen and helium, left over from the Big Bang. But each generation of stars has added to the cosmic inventory of heavy elements. Carbon, nitrogen, and oxygen are produced in large quantities by massive stars and dispersed in supernova explosions. Elements like iron are also produced in supernovae, both in the core collapse explosions of massive stars and in the thermonuclear explosions of white dwarf stars in binary systems. Even heavier elements, like gold and platinum, are thought to be produced primarily in the collisions of neutron stars, exotic objects so dense that a teaspoonful of their matter would weigh billions of tons. This gradual enrichment means that stars forming today have much higher abundances of heavy elements than stars that formed billions of years ago. This has important consequences for planet formation, as heavier elements are essential for building rocky planets and the complex molecules needed for life. The Sun has roughly twice the abundance of heavy elements as the average star in the galactic halo, reflecting the fact that it formed relatively recently from gas that had been enriched by billions of years of stellar evolution. Planets like Earth simply could not have formed in the early universe because the necessary elements did not yet exist in sufficient quantities. The future evolution of the Milky Way, beyond the eventual merger with Andromeda, is difficult to predict in detail, but follows some general principles. Star formation will gradually slow as the galaxy's reservoir of gas is depleted. Some gas will be locked up in long-lived stars, some will be ejected from the galaxy by energetic processes, and some will be converted into stellar remnants like white dwarfs, neutron stars, and black holes. Over tens of billions of years, the galaxy will slowly fade as massive bright stars die off and are not replaced, leaving behind a population dominated by small, dim, long-lived red dwarf stars. Eventually, even the longest-lived stars will exhaust their fuel. Red dwarf stars, the smallest and coolest stars capable of sustaining nuclear fusion, can burn for trillions of years, far longer than the current age of the universe. But eventually, they too will run out of hydrogen and fade away, becoming dim, cooling white dwarfs. Over timescales that are almost impossible to comprehend, measured in countless trillions of years, the Milky Way will become a dark, quiet place, filled with the remnants of dead stars slowly cooling toward absolute zero, orbiting in the gravitational well of the central supermassive black hole. But even that is not the final state. Over unimaginably long timescales, the galaxy itself will evaporate as stars occasionally pass close enough to each other to gain enough energy to escape the galaxy's gravitational pull entirely. This process, called evaporation, will take perhaps 10 to the 20th power years, a number so large that it is difficult to give it proper context. For comparison, the universe is currently less than 10 to the 10th power years old. The evaporation of galaxies will occur over a timescale a billion times longer than the current age of the universe. The supermassive black hole at the center will eventually be all that remains, slowly growing as it occasionally captures a passing stellar remnant. But even black holes are not eternal. According to quantum mechanics, they emit a faint radiation, known as Hawking radiation, after the physicist Stephen Hawking who predicted it. This radiation causes black holes to slowly lose mass, evaporating over timescales that make even the evaporation of galaxies seem quick by comparison. A black hole with the mass of Sagittarius A star will take approximately 10 to the 99th power years to completely evaporate, a number so vast that it defies meaningful comprehension. In this far distant future, the universe will be a cold, dark, almost empty place. The expansion of the universe, driven by dark energy, will have carried distant galaxies so far away that they will no longer be visible from what was once the Milky Way. The cosmic microwave background will have cooled to temperatures only a tiny fraction of a degree above absolute zero. Its photons stretch to wavelengths of meters or kilometers. Entropy will have increased to nearly its maximum possible value, and the universe will approach a state of equilibrium where nothing interesting can happen, a condition sometimes called the heat death of the universe. But these are concerns for a future so distant that it is almost meaningless to contemplate. For now, the Milky Way is alive and vibrant, full of stars and planets, gas and dust, black holes and nebulae, all interacting through the fundamental forces of nature. Our Sun is halfway through its main sequence lifetime, steadily burning hydrogen in its core, providing the energy that sustains life on Earth. Earth itself is approximately 4.5 billion years old, and life has existed on its surface for most of that time, slowly evolving through countless generations, adapting to changing environments, surviving mass extinctions, and eventually giving rise to complex organisms capable of contemplating the universe itself. The galaxy contains hundreds of billions of stars, and many of those stars likely have planets orbiting them. Some of those planets may be similar to Earth, located in the habitable zone of their parent star, with liquid water on their surfaces and atmospheres that could support life. The exact fraction of stars with Earth-like planets is still unknown, but recent discoveries suggest that such planets are common. If even a small percentage of those planets develop life, And if even a tiny fraction of those go on to develop intelligent life, then the Milky Way could be home to many other civilizations, perhaps thousands or even millions of them spread across the vast expanse of the galactic disk. The distances between stars make direct contact between such civilizations extraordinarily difficult. Even traveling at a significant fraction of the speed of light, journeys between stars would take years or decades at minimum, and more likely centuries or millennia. Communication by radio waves or other forms of light is faster, traveling at the speed of light itself, but even so, conversations between civilizations on opposite sides of the galaxy would involve delays of tens of thousands of years for each exchange. The galaxy is simply too vast for easy interaction between its inhabitants. Nevertheless, the possibility of other life existing somewhere in the Milky Way is tantalizing. Humans have been searching for signals from other civilizations for decades, listening with radio telescopes for any sign of artificial transmissions that might indicate the presence of other intelligent beings. So far, we have found nothing definitive. But the search continues, and the silence does not necessarily mean that we are alone. Perhaps other civilizations are also listening, waiting for someone else to break the silence. Perhaps they are so different from us that we would not recognize their signals as artificial. Perhaps they existed millions of years ago and are now extinct. Or perhaps they have not yet evolved to the point where they can build radio transmitters. The universe of possibilities is vast, and our knowledge is still limited. What we do know is that the conditions that allowed life to develop on Earth are the result of a long chain of events that stretches back to the very beginning of the universe. The Big Bang created the hydrogen and helium from which the first stars formed. Those stars forged the heavier elements in their cores and scattered them into space when they died. Those elements mixed with new generations of gas, forming new stars and planets, including our Sun and Earth. The energy from the Sun, steady and reliable over billions of years, allowed life to emerge and evolve on Earth's surface. The stability of our solar system's architecture, with Jupiter acting as a gravitational shield that deflects many comets and asteroids away from the inner planets, has protected Earth from excessive bombardment. The presence of the Moon has stabilized Earth's axial tilt, preventing wild swings in climate that might have made life's development more difficult. All of these factors, and many more, have contributed to making Earth a place where life could not just emerge, but thrive and diversify. The Milky Way has been our home for as long as Earth has existed, providing the materials from which our planet was built, the energy that powers our Sun, and the gravitational environment that keeps our solar system stable. We are, in a very real sense, children of the galaxy, made of atoms that were forged in the hearts of stars that died long before our Sun was born. The iron in our blood, the calcium in our bones, the carbon in our cells, all of it was created in stellar furnaces and scattered into space to eventually become part of the molecular cloud from which our solar system formed. When we look up at the night sky and see the pale band of light that gives the Milky Way its name, we are looking at our galaxy from within, seeing the combined light of billions of stars too far away and too dim to be resolved as individual points. That band of light has been visible to humans throughout our entire history, and every ancient culture that looked up at the night sky wondered about its nature. The ancient Greeks called it Galaxias Kyklos, the Milky Circle, which eventually gave us the word galaxy. They imagined it as spilled milk from the breast of the goddess Hera. Other cultures saw it as a river or a path or a bridge between worlds. It was not until the early 17th century that Galileo Galilei turned his newly invented telescope toward the Milky Way and discovered that it was composed of countless individual stars, too faint to be seen with the naked eye, but clearly visible through his telescope. This was one of the first hints that the universe was much larger and more complex than had been previously imagined. Over the following centuries, astronomers gradually pieced together the structure of our galaxy, mapping the distribution of stars and gas, measuring distances, and determining that the Sun was not at the center of the Milky Way, but rather located far out in the disk. In the early 20th century, the astronomer Harlow Shapley used observations of globular clusters to map out the structure of the Milky Way and determine the Sun's position within it. He found that the globular clusters were distributed in a roughly spherical halo around a point in the constellation Sagittarius, and he correctly concluded that this must be the center of the galaxy. This placed the Sun about 25,000 light-years from the galactic center, a distance that has since been refined to approximately 26,000 light-years based on more detailed observations. At around the same time, Edwin Hubble was making observations that would revolutionize our understanding of the universe. He observed galaxies beyond the Milky Way, determining that they were separate island universes in their own right, not nebulae within our own galaxy as had been previously thought. He also discovered that these galaxies were moving away from us, with more distant galaxies moving faster than nearer ones, a relationship now known as Hubble's law. This discovery provided the first clear evidence that the universe was expanding, leading to the development of the Big Bang theory and our modern understanding of cosmology. Today, we can observe the Milky Way across the entire electromagnetic spectrum, from radio waves to gamma rays. Different wavelengths reveal different aspects of the galaxy's structure and activity. Radio observations show us the distribution of cold hydrogen gas and the locations of star-forming regions. Infrared observations can penetrate dust clouds that block visible light, allowing us to see into the dense cores of molecular clouds and the crowded regions near the galactic center. X-ray observations reveal hot gas and the remnants of supernova explosions, as well as the energetic environments around black holes and neutron stars. Each wavelength provides a different perspective on the galaxy, and by combining observations across the spectrum, astronomers can build a comprehensive picture of the Milky Way's structure, composition, and evolution. The study of the Milky Way is not just an academic exercise. Understanding our galaxy helps us understand the broader universe, because the processes that shape the Milky Way are the same processes that shape galaxies throughout the cosmos. By studying star formation in nearby molecular clouds, we learn about star formation in galaxies billions of light-years away. By mapping the distribution of dark matter in the Milky Way's halo, we gain insights into the nature of dark matter throughout the universe. By tracking the motions of stars near the galactic center, we learn about the behavior of gravity in the extreme environments around supermassive black holes. Moreover, understanding the Milky Way gives us context for our own existence. We are not separate from the galaxy, we are part of it, intimately connected to its history and its future. The atoms in our bodies were forged in stars that lived and died before the Sun was born. The energy that powers our civilization comes ultimately from the Sun, which itself is a product of the galaxy's ongoing cycle of star formation and evolution. Our future, at least for the next few billion years, is tied to the Milky Way's fate, and understanding that fate helps us understand our own place in the cosmos. As we drift towards sleep, it is comforting to remember that we are part of something much larger than ourselves, something ancient and vast and beautiful. The Milky Way has been here for more than 13 billion years, long before Earth existed, long before the Sun was born. It will continue to exist for billions of years into the future, slowly evolving, gradually changing, but maintaining its essential character as a vast, rotating disk of stars and gas, held together by gravity and illuminated by the light of hundreds of billions of suns. In the grand scheme of the universe, each of us is small and our lives are brief. but we are also participants in a story that began with the Big Bang and will continue for eons to come. We are made of stardust, assembled over billions of years through the patient work of gravity and nuclear fusion. We are the universe contemplating itself, matter that has become conscious and aware, capable of understanding the processes that brought us into being. This is perhaps the greatest wonder of all, that the universe has evolved in such a way that parts of it can look back and understand the whole. That atoms forged in ancient stars can arrange themselves into brains capable of comprehending the cosmic history that created them. The Milky Way continues its slow rotation through space, a spiral of light in the darkness, home to hundreds of billions of stars and possibly countless worlds. It is a place of birth and death, creation and destruction, change and continuity. It is old beyond imagining, yet young compared to the future that stretches ahead. It is vast beyond human comprehension, yet intimate in the sense that it is our home, the cosmic environment that has nurtured us and made our existence possible. As we close our eyes and let our thoughts drift toward rest, we can picture the galaxy turning slowly in the darkness, its spiral arms trailing outward from the glowing center, each arm studded with the light of young stars and glowing nebulae. We can imagine the quiet regions between the arms, where older stars move on their patient orbits, carrying their retinues of planets through the emptiness. We can envision the halo of globular clusters and ancient stars surrounding the disk, remnants of the galaxy's earliest days. We can picture the dark matter halo, invisible but essential, holding everything together with its gentle, gravitational embrace. And somewhere in this vast structure, on the edge of a minor spiral arm, orbiting an ordinary yellow star, is a small blue planet where life has flourished for billions of years. This planet, our home, drifts through space as part of the solar system, which itself moves through the galaxy, which itself moves through the expanding universe. We are in motion on scales we cannot feel, participants in a cosmic dance that has been ongoing since the beginning of time. The night sky above us, when we can see it clearly away from artificial lights, is filled with the light of the Milky Way. That band of light stretching across the darkness is the combined glow of billions of stars, each one a sun in its own right, many of them accompanied by planets we cannot see. Some of those stars are younger than our sun, some are older, some are larger and brighter, some are smaller and dimmer. Each one is a unique object with its own history and its own future. Yet all of them together form the galaxy, a system so large that light takes 100,000 years to cross from one side to the other. The scale is difficult to grasp with our limited human minds, evolved to deal with distances we can walk and times we can measure in lifetimes. 100,000 light years is a distance that has no direct meaning to us, no equivalent in our daily experience. Yet it is real and it can be measured, and it describes the actual size of the structure within which we live. To travel from Earth to the galactic center, even at the speed of light, would take 26,000 years. A message sent to the galactic center today would not arrive until more than 26,000 years from now, and a reply would not reach us for another 26,000 years after that. The round-trip communication time exceeds the entire span of recorded human history. Yet despite these vast scales, there is an underlying unity to the galaxy. All of its stars are bound together by gravity, all orbiting the common center of mass, all participating in the slow rotation that gives the galaxy its spiral structure. Gas and dust flow through the disk, enriched by the deaths of old stars, providing the material for new stars to form. Energy flows outward from the galactic center, carried by radiation and stellar winds and supernova shockwaves. Matter and energy are constantly being exchanged and recycled, creating a dynamic equilibrium that has persisted for billions of years. This equilibrium is not static. The galaxy is evolving, albeit slowly. Star formation was more vigorous in the past and will gradually decline in the future as the reservoir of gas is depleted. The abundance of heavy elements continues to increase with each generation of stars. Small satellite galaxies are occasionally captured and absorbed, adding their stars to the Milky Way's population. The central supermassive black hole grows slightly larger each time it captures a passing star or gas cloud. All of these changes are incremental, but over billions of years, they accumulate into significant evolution. Yet through all these changes, the basic nature of the galaxy remains constant. It is a place where gravity and nuclear fusion, the two fundamental processes that drive galactic evolution, continue to work their patient magic, creating order from chaos, structure from uniformity, complexity from simplicity. Stars form, burn, and die. Elements are forged and scattered. Planets coalesce and orbits stabilize. Life, at least on one small blue planet, emerges and evolves and wonders about its place in the cosmos. The future of the Milky Way, as we have seen, stretches forward for times that dwarf its past history. The eventual merger with Andromeda will be a dramatic event, but it is still billions of years away. Time enough for countless more generations of stars to be born and die. Time enough for whatever civilizations exist in the galaxy to rise and fall many times over. After the merger, the combined galaxy will slowly age, its star formation declining, its population of bright, massive stars dwindling, until eventually it becomes a collection of dim red dwarfs and stellar remnants, faintly glowing in the darkness of a cold, expanding universe. But that, too, is far in the future. So far that it is more imagination than prediction. For now, in this present moment, that is all we truly have. The Milky Way is a vibrant, living galaxy, full of activity and light. Stars are being born in the Orion Nebula and in countless other star-forming regions throughout the disk. Supernovae are exploding, scattering heavy elements into space and triggering new rounds of star formation. The supermassive black hole at the galactic center occasionally flares as it consumes a bit of nearby gas. Planets orbit their stars, some perhaps harboring life, others barren and lifeless. The cosmic dance continues, as it has for more than 13 billion years, as it will for billions more to come. We are privileged to be aware of all this, to understand our place in the galaxy and the galaxy's place in the universe. For most of history, humans looked up at the night sky and could only wonder. They created myths and stories to explain what they saw, imagining gods and heroes among the stars. They used the regular motions of the celestial objects to create calendars and navigate across land and sea. But they did not know what stars were made of, or how far away they were, or that the Milky Way was just one galaxy among billions in a vast universe. Now we know. Through centuries of patient observation and careful reasoning, through the development of powerful instruments that extend our senses far beyond their natural limits, through the application of mathematics and physics to understand the fundamental laws that govern the cosmos, we have built up a comprehensive picture of the universe we inhabit. We know how stars work. We know how galaxies form and evolve. We know the history of the universe from the Big Bang to the present day. We have sent spacecraft to visit other planets in our solar system, and we have detected planets orbiting other stars. We have peered back in time by looking at distant galaxies, seeing them as they were billions of years ago when the universe was young. This knowledge is one of humanity's greatest achievements, a testament to our curiosity and our ability to understand the natural world through observation and reason. It is a collective achievement, built up over many generations, with each generation adding to what came before. the ancient astronomers who tracked the motions of planets, the Renaissance scientists who first used telescopes to explore the heavens, the 20th century cosmologists who worked out the Big Bang Theory, the modern astronomers who have mapped the structure of the Milky Way and detected planets around other stars. All have contributed to our current understanding, and that understanding continues to grow. New telescopes, both on the ground and in space, continue to reveal new details about the Milky Way and the broader universe. Advances in computing power allow astronomers to create ever more sophisticated simulations of galactic evolution, testing theories against observations and refining our models of how galaxies work. New instruments can detect gravitational waves, ripples in space-time itself, allowing us to observe the universe in an entirely new way and witness events like the collisions of black holes and neutron stars that would otherwise be invisible. There is still much we do not know. The nature of dark matter remains mysterious, despite decades of searches for the particles that might compose it. Dark energy, which drives the accelerating expansion of the universe, is even more enigmatic. The exact mechanisms that regulate star formation are still being worked out. The full history of the Milky Way's formation and evolution is still being pieced together from observations of old stars and computer simulations. The question of whether life exists elsewhere in the galaxy remains unanswered, though the discovery of thousands of exoplanets has shown that planets are common and the conditions necessary for life probably exist in many places. These unknowns are part of what makes science exciting. Each answer leads to new questions. Each discovery opens up new areas to explore. Our understanding of the universe is not fixed, but continually evolving, growing more detailed and comprehensive with each passing year. Yet even as we learn more, we also become more aware of how much we still do not know, how vast the universe is, and how limited our current understanding remains. This is not a cause for despair, but for wonder and excitement, because it means there is always more to discover, always new questions to ask, always new mysteries to solve. As we settle into sleep, these thoughts can bring a sense of peace and perspective. The universe is vast and ancient, operating on scales of space and time that make our individual concerns seem small by comparison. Yet we are not separate from this universe. We are part of it, products of its long evolution, participants in its ongoing story. The atoms in our bodies have been through the hearts of stars, through the cold of interstellar space, through the formation of the solar system and the early history of Earth. We carry within us the history of the cosmos, written in the very substance of which we are made. The Milky Way, our galactic home, will continue its slow rotation through space long after we are gone. The stars will continue to shine, new stars will be born, old stars will die, and the great cycle will continue. The galaxy does not notice us, does not care about our existence, yet it has made us possible. Without the billions of years of stellar evolution that created the heavy elements, without the stable galactic environment that allowed our solar system to form and persist, without the ongoing processes that maintain the conditions necessary for life, we would not be here. In that sense, the galaxy has given us everything, and we owe our existence to its long history and its patient operation of the laws of physics. So let us rest, secure in the knowledge that we are cradled within a vast cosmic structure that has existed for billions of years and will continue for billions more. Let us take comfort in the stability and order of the universe, in the reliable operation of natural laws that govern the motions of planets and the burning of stars. Let us appreciate the beauty of the night sky, the pale band of the Milky Way stretching across the darkness, each point of light a distant sun with its own story to tell. The galaxy turns slowly in the night, indifferent to our presence, yet essential to our existence. Stars are born in clouds of gas and dust, lighting up the darkness with their nuclear fires. Planets orbit those stars, some perhaps harboring life, others lifeless and cold. The supermassive black hole at the galactic center sits quietly, dominating the motions of nearby stars through its immense gravity. The dark matter halo surrounds it all, invisible but essential, holding the galaxy together with its gravitational embrace. And on one small planet, orbiting an ordinary star in an unremarkable part of the galaxy, conscious beings look up at the night sky and wonder about their place in the cosmos. They ask questions about the nature of reality, about how the universe began and how it will end, about whether they are alone or whether other beings exist somewhere in the vast darkness. They build telescopes and spacecraft. They develop theories and test them against observations. They slowly piece together an understanding of the universe that is both humbling and inspiring. We are those beings, and this is our moment in cosmic history. We exist in a quiet period between the violent early universe and the cold, dark, far future. We live on a planet that has been blessed with the conditions necessary for life, orbiting a star that has been stable for billions of years and will remain so for billions more. We inhabit a galaxy that is old enough to contain heavy elements, but young enough to still be forming new stars. We are, in many ways, fortunate to exist when and where we do. As sleep approaches, let these thoughts carry you gently into rest. Picture the Milky Way in your mind, a great spiral of light turning slowly in the darkness. Imagine the billions of stars scattered throughout its disk, each one a sun, many of them surrounded by planets. Think of the vast clouds of gas and dust, the star-forming regions where new stars are being born even now, the remnants of dead stars enriching the interstellar medium with heavy elements. Visualize the dark matter halo, invisible but omnipresent, providing the gravitational foundation for all this visible structure. See yourself as part of this grand structure, not separate from it, but intimately connected to it. You are made of material that was forged in stars, organized by billions of years of cosmic evolution into a form capable of consciousness and thought. You are the galaxy looking at itself, a small part of the cosmos that has become aware and is trying to understand the whole. This is a profound and beautiful thing, a source of wonder that can bring peace to a restless mind. The universe is vast, but it is also comprehensible. Its scale is enormous, but its laws are simple and can be understood. It has existed for nearly 14 billion years, and it will continue to exist for eons to come. But this moment, right now, is also part of that story. You are living in the universe's history, participating in its evolution, even if only in the smallest way. Your thoughts and actions are part of the cosmic narrative, brief but real, fleeting but meaningful. So rest now, secure in your place within the Milky Way, within the universe, within the grand story that began with the Big Bang and continues to unfold around us. Let the knowledge of the cosmos bring you peace. Let the vastness of space and time put your worries into perspective. Let the beauty of the galaxy fill you with wonder and contentment. The stars will continue to shine. The galaxy will continue its slow rotation, and the universe will continue its expansion, all operating according to the same physical laws that have governed the cosmos since the very beginning. Sleep well, child of the stars, inhabitant of the Milky Way, temporary manifestation of the universe's long evolution. You are part of something ancient and vast and beautiful, something that will continue long after you are gone, but that is also present here and now, in this moment, in this place. The galaxy holds you in its gentle gravitational embrace. The Earth beneath you is made of atoms forged in stellar cores. And the thoughts in your mind are possible because of billions of years of cosmic evolution that created the conditions for life and consciousness. All is well in the cosmos. The stars burn steadily, the planets orbit reliably. The galaxy turns with patient grace. The universe expands, but it does so gradually, at a pace that will not affect us for billions of years. The laws of physics operate consistently, creating a stable, predictable environment where matter can organize itself into stars and planets and eventually life. The story that began with the Big Bang continues, and we are privileged to be conscious participants in this ongoing narrative, able to observe and understand and appreciate the magnificent structure of which we are a part. Let this knowledge bring you peace as you drift into sleep. The Milky Way is your home, the galaxy that has nurtured you and made your existence possible. It will continue long after you are gone, but it is also here now, surrounding you, supporting you, connecting you to the long history of cosmic evolution that stretches back to the beginning of time. You are safe within its embrace, a small but meaningful part of a vast and ancient structure that has been evolving for more than 13 billion years and will continue for billions more to come. Rest now in the knowledge that you are part of the Milky Way, and the Milky Way is part of you. The atoms in your body came from stars. The energy that powers your thoughts comes ultimately from the sun, which is itself a product of the galaxy's ongoing cycle of star formation and evolution. You are connected to the cosmos in the most fundamental way possible, made of the same material, governed by the same laws, participating in the same great cosmic story that encompasses all of existence. The galaxy continues its slow dance through the universe, a spiral of light in the darkness, home to hundreds of billions of stars and possibly countless worlds. It is ancient and vast, yet also intimate and familiar, the cosmic environment that has shaped us and made us what we are. As you sleep, it turns slowly through space, carrying you and everything you know on a journey that began billions of years ago and will continue for billions more. Rest well, knowing that you are part of this grand cosmic structure, this beautiful galaxy that we call home. Good night.